because it's computing it a little differently. There's, different round off errors, that type of thing. It may not balance the same way that it balanced within the other computational systems. But we'll obviously start with what Culver did and see if we can replicate those equations. I know Brendan talked about that. So that's sort of like the second big step. We'll go into the details, and we'll get Brendan's input when we do.
Are you going to simulate in 2 or 3 dimensions in OpenFOAM?
So I'm just talking about the steps to get everybody started. So we have to get an AWS build that everybody can then access and bring up in their own way without having to do much of an install. I mean, that's part of the motivation for this. The next one is try and get the Model G equations into OpenFOAM. I know Brendan's been working on that, but then we want to add that to the build. They have builds called an AMI. So then everybody has that set of equations to start with, so that people don't have to do anything. The people don't have to put the equations in. The build already has everything there. And then, and this is what Matt did a whole bunch of. He did some searching for parameters in order to try and get, particles to form or solitons to form. And then, the next step would be searching for other types of particles besides having a neutron, trying to get an electron, proton, and even some of the transient particles that the particle physicists look at, or some variants of transient particles that last for a short period of time. Exploring parthenogenesis. I mean, people have been talking about that. So that's another thing. Vortical motion, and that's sort of like the name for the group. So we want to, see if we, first we have to get see the motion coming out of the OpenFOAM, and then see if we can see vortical motion, and then, play with a number of things. And we've been talking about playing with different things. So I'm just trying to capture all the things we talked about. Light also, there's a couple of different things that we have with the Model G. We also have light. And so the reactions that are happening have to create some type of vortical light motion, because we have EM waves, as opposed to the reactions twisting in and creating particles. They go in a line and create, light waves. So we have to try and model that, including, things like double slit experiment, the types of gradations of behavior when you have the solid particles and you have these light waves going by them. How do they then split when you get a double split, so that you create those gradation light patterns, that you create those gradation waves. Automating the search. I've got some tools that can help you do, pull results out of experiments, do a little bit of reasoning on them, and then rerun the experiment in an automated fashion. I have some tools to do that. But they're not necessarily built for Linux, they're built for Windows. So I don't know if we want, OpenFOAM and that type of stuff run on Linux, so we have to do some type of connector. And then there's all these other things, and this is what Michael talked about earlier. There's all sorts of other computational tools for reaction diffusion. There's all different types of mathematical methods. There's all different types of experiments that can be run, and that includes the gravitational experiments, the EM experiments that Paul's been working with a lot of people on. It also touches on a lot of the, I wouldn't say esoteric, because you got scientists, physicists, and other people, biologists, that are experimenting with ether type behaviors that they're seeing, and that goes back for hundreds of years. The best source for that, I would say, would be Claude Swanson's book, because there's been a whole bunch of experiments, but there's a lot of other variation beyond what he's talked about. Correlating simulation and models with phenomenon. So we have all those experiments. How do those experiments then correlate with all of these simulations that we've been doing, including the variations on reaction and diffusion computational simulations? And note that there's 2 different types of things that we're looking at here. We're looking at both the physical model and the computational model, and you don't have to have a hit on both. I mean, that's the best thing. But if we can come up with good physical models that describe the behavior, that's a major step in and of itself. And then coming up with computational models around those physical And note, you can have multiple different computational models associated with specific physical models. And I think you can do the same the other way around too. I know you can do the other way. So even with one computational model, that you can have several different physical models that are different around it. Okay, so that's the high level. You know, go ahead and throw out some comments, and we'll dive down into the details of each step.
I just wanted to ask for AWS, can you use it without cost, or does it always cost something?
All right, so your first instance, if you use their instance, I believe it is free. If we're going to be making our own, it's like $5 a month, okay? And that first one's free. So you could, I think, create your own, and then, you know, you might be starting to get a $5 a month charge. But the thing about it is you can turn it off, because you can be charged by the minute, by the hour, by the day. And that's done automatically. So if you do your experiment and then turn it off, and you're only running experiments on the weekends, then you're probably going to get charged maybe $1 or $2 a month. So, you know, you can do as much as you want, and we're going to try and set up the AMI so that they're scalable, so that you know, you can run a heavier one, and, you know, be a higher cost, but you can turn it off. You know, and we'll put that in the instructions there once we create the AMI builds on how to do all of that.
Okay, and have we allocated anybody to do the builds for AWS? You know,
Well, different people have been doing different things. So I know Brendan has been doing some open foam. You know, he's been trying to do some of those builds. We can move that over to AWS.
Well, what do we want to like get it tested out on a local computer first before we want to go to something computationally? Or just work it out in principle. Just verify that it's something that's going to work. Like, I'm not even sure that we'd be able to do this simulation in OpenFOAM, from my knowledge, but I'm not very knowledgeable, so.
So the reason why we're picking OpenFOAM, because it's free, open source. It's the most popular variant for fluid dynamics.
and we're just trying it out. We're just trying it out first to see if we can get anywhere with it.
Yes, but I have a question here that
we can add reaction diffusion to it.
I mean, you have like a lot of different vacuum constituents, but in OpenFOAM you can only have one fluid simultaneously. How do you model that?
So we're looking at general fluid modeling tools, and there's two of them that I know of. There may be others, but I haven't been able to find others. The predominant ones are OpenFOAM, and then Blender is another free tool. And I've seen that it has some fluid dynamics represented. I've seen them having add-ons for that. And I think I've also seen reaction diffusion.
One fluid system.
Right. And the reason why we want a fluid system, because we want to see motion.
Well, what's David saying?
Yeah, I can't hear you too, but we can't hear you, David.
Yeah, I'm on a train station here, so there might be a little noise here.
Why don't you repeat what you said?
Yeah, I can do that. I mean, as I imagine, you have a lot of vacuum or ether constituents, and if they are supposed to flow independently of each other, then I would say some other system has to be used, because OpenFOAM and traditional fluid dynamic systems only are one fluid systems.
Well, what you're trying to say is that we have etherons of different types, whereas that would be only for etherons of the same type?
No, the OpenFOAM, okay, so OpenFOAM, Blender, they can represent different types of substances within it, particularly when we're talking about reaction diffusion systems. So that's part of the mix when you're talking reaction diffusion, but it's also part of the mix with OpenFOAM. I looked at that, and yes, it's there. I believe it was in Blender too, in these add-on packages. So that's part of it. That's not something that's being missed from it.
What about density? I mean, usually that's a key parameter.
They've got density, and that's part of the, where are the particles and how are they moving? That's all part of this standard type of tool. That's why we're looking at this type of standard tool, because it has those features, particularly because they've added reaction diffusion.
Well, but we're kind of, that's traditional fluid dynamics, which is handled more or less on a macroscopic scale. But we're on the subquantum here, so I mean, and we're not even.
It's all some type of particle or subparticle. Okay.
I was just wanting to finish. Is that so far no instance of mass has been presented as part of this model, and that's typically, macroscopic fluid dynamics involves mass. So,
I've looked at these systems, and to the best of my recollection, they did include some of those elements. Now, will we have to create our own mathematical system that adds more and more of these features? It's easier to take the existing software, because it's open source, and add those features in. But I believe that people have already added those features into both of these.
We have to sort of like play around with it just to see.
Right. We have the freedom with an open source system to add those features. Now, one of the things that, Michael, you brought up at the beginning is, a potential concern, and that is the computational running time. Okay. Now, typically within a package like this, there's parameters, so you can simplify the computation. You can play with the parameters. I mean, because when they break up a fluid, and they have all of these particles in there, they say, okay, this is a subgroup, this is a subgroup, this is a subgroup, this is a subgroup, and they break it into many, many, many different subgroups, but not too many. Okay, they don't look at everything at the particle level. They take a group, okay, a subgroup. Okay, because you can't do it when you do it every single subparticle, because the computation won't happen. So they break it into subgroups. So they have parameters to change the number of subgroups and how they're geometrically connected to each other. So that's how this type of computation, finite element analysis, done the same way. So they break things up into subgroups and do the computations on the subgroups that, as closely possible, mimic what's happening at the particle level. And the computational science, they have to sit down there and see how well they map. So that everything that you've been talking about so far is something that's typically covered. And in some cases, yes, we might have to create some add-ons, but we'll probably have to play with the parameters to, make the groupers a little bit bigger in order to do the computation. And if the computation is too heavy, we may have to go to some other computational system that's even simpler. And when I looked for reaction diffusion systems, people had done that. They had used very much simpler and alternative methods to do it. And they don't have all the flavor, all the visualization. They don't have all the extra add-ons. I'm just, suggesting OpenFOAM because it's got that type of stuff.
Did anyone check the link I sent on the Brucillator?
Yeah, I had a look at that. I didn't go into it very much. I just saw the link and checked it out a bit.
That's a two-dimensional simulation, and I suppose it might be a good basis to rewrite for Model G.
Are you talking about a link you sent like 2 or 3 weeks ago?
No, just some days ago, the latest week.
Okay, I may not have looked at that one if it was just a couple days ago.
I think
it's pretty easy to miss a lot of this communications on Facebook. I tend to myself.
So one of the things that you're going to see with this type of environment like OpenFOAM or another open source is you're going to see people have created all these add-ons and things associated with it. So here, here's all the different types of sizes of servers that you can be using. So it's, they have very different costs, like $2 per hour versus 68 cents per hour, that type of thing. And some of these are large. Okay, if you're just playing with it at the basic level, you're going to use a small. The cost is going to be much cheaper. But if you're doing the production test, you know, that we're looking at doing, then these are some of the costs, and then you turn it off and the costs aren't there anymore. So he's tested many different types of servers to see which ones are best for OpenFOAM in general. And then of course, for our specific problem, we may find that, you know, there's another build that's more, you know, than the one he came out with as being more efficient. So people have done this analysis and say, okay, if you've got 5 of them, not so good, but once you get to, you know, about 10, you know, adding to 30, 40 of them doesn't really add any.
I've got a message just come up saying this meeting will end in 10 minutes. So if it does end, I will start a new one and put it on Facebook.
Great. Okay. So we need to start with something, and having one person doing the test, we could wait for that person to say, okay, we're good. Or we could have one person, you know, get some stuff working and say, okay, here, I've got a build. Now everybody, instead of you guys having to do your own builds, I'm going to share my build with you. And we can work on that. And then everybody can be working the same thing. And if we find that OpenFOAM doesn't work, then we can do the same task with Blender. And if Blender doesn't work, there might be a third one out there. I don't recall. I think I might have seen one. Or we could start going to, you know, ad hoc software, or we can try and modify OpenFOAM. We can go into the code and add whatever features we want to it.
Justin,
so there's a lot of different directions.
Once, if I say I've got it installed correctly and the build is correct and it's up and running, OpenFOAM, what then? Do I then send it to you or send it to this site, and then it puts on the cloud?
All right. So you're doing it on your own machine. We're going to have to take all the steps that you've done and replicate them on one of these OpenFOAM builds. Okay. So we'll just take, you know, what they suggested and follow their steps and build it up in AWS, and then add your, you know, addition to that. And then we'll make an AMI, and then that AMI we can share with each other, and each one of us will be able to bring that up.
There's quite a good CDF online forum which works with OpenFOAM, and it has things like, if you're having trouble with OpenFOAM installation, you can post a message and someone usually replies after
so that's a big advantage of using a system like that, is there's a whole community out there to leverage. There's tools and things like that, and we can get into the code if we want to add anything ourselves. So great questions, very valid questions. I don't know if I've addressed all of them. I don't know how much you guys have, you know, I'm trying to give you some of my knowledge and my experience working with all these different computational systems, because, you know, my PhD's in that area. And, you know, so I have a breadth of, you know, many years after that of working with computational systems. So I'm trying to give you some of that breadth, that all the things you brought up are valid. And they've been asked by other people and done by other people, because when you look at a system like OpenFOAM, everybody's using it for very different reasons, very different purposes. And so you see those types of things being put in, and it's open so that people can put that type of stuff in. I'm not pushing OpenFOAM. I'm basically talking about basic principles of this type of computational system. So I'm just talking about the advantages and disadvantages. That's it.
So I have a question then about the OpenFOAM. So can you model massless systems?
Typically, because mass is an additional computation, typically that's not something that's added in, typically with these systems, if I recall. But I think I've seen both.
They probably would have mass. You know, they seem to be using gas law equations for the examples. But just kind of like
I believe it's an extra parameter, but I believe that you can do that. It's setting the parameters, and if you set almost nil for that type of parameter, then it's basically you're doing massless. So, I believe I've seen these variants that you've talked about in my looking at both Blender and OpenFOAM. So I've seen the discussion, the questions that you brought up. I've seen those discussions and people talking about how to do it one way or another.
It's just like running an arbitrary program. So it's not motivated by a realistic thing. We're just starting with an arbitrary put in a certain amount of mass, average velocity, and see how the system initiates it. See how the tutorials initiate the system. There'll be the R1 will probably be initiated a similar way. Put in a mass, and then or play around with it till you get a certain mass, and then see how it runs. And then from there, you can perhaps at some stage fit it to something more realistic.
So another big thing is to make sure that our build has Pulver's code on it, so we can run that too, as an example. So everybody has access to it and can run it on their own. Creating an AMI that's sort of like, okay, we've got a build, it's good, we want to replicate it very easily, as opposed to doing all the build steps.
You know, you have to rebuild for every change you make to the model, since the initial values are put into the C++ code.
So there's two different things. One, you can have a basic build, and then you can have, I'm not directly answering your question, but your question is related to other stuff, because you can have a basic build, but then there's a whole bunch of additional things that you can add, and you can have separate scripts to add those additional things on. And that's sort of like
you have to rebuild for every new initial setup. That's how
that's part of the basic research. So we've got this build, then everybody's got to put in different parameters and run them. And then you change the parameters, run again, change the parameters, run again, change the parameters, run again. But that's
no, it doesn't work like that. It doesn't work like that. You have to rebuild for each change of parameters.
OpenFOAM, you have to do a rebuild.
Yeah, you set the initial conditions in the C++
Okay,
code.
so there's different things that you're rebuilding. One is the server. Two is the, it's like compiling a program. Okay, so you have to build the server. You have to put
and run it a lot, so I know how it works.
You have to build the server. You have to add OpenFOAM software in general. There's a whole bunch of additional add-ons that you might have to build. So all of that is one thing that is fixed. Then you've got, let's say the specific program that you're going to run, and you have to build that. So there's many levels of builds that can be shared. That final build that you're talking about is sort of like the last add-on thing that you're going to be running. Okay, so there's a huge amount of this build that can be so when I talk a build, I'm talking about all this stuff pre-work, like getting the server up, installing OpenFOAM, and adding all those additional features. And then once you got everything set, once you have the equations in, okay, you already have them stored in a location, and you already have them as part of your definition file. Then you click the build, and then you run the build, which is the simulation. Those final two steps that you're talking about, yes, you're going to have to do that each time. But all those other steps you won't have to do each time, because that can be the package that we're using. You can add Terraform. I don't want to get into Terraform because that's getting too complex. But there's others, other build scripts can be created. I'm just going to put it that because in this case, build can mean, the operating, the infrastructure, the software, or just the, it can be the, model that you're specifically working with. Okay, it can be a whole bunch of different things. So we can add all of that in
to rewrite so that you have one build and just can change the initial setup separately.
But there's going to be some basic definitions before you run your build of because when you're creating a computational system, you have some parameters, and those can be files in there that we already have. And then, you hit the final build for, the simulation you're going to run, and then you hit the simulation. And then you can pull, different types of views out of the simulation, and we can have parameters for all of those. So all of those different things can be put in scripts in the AI build that we're working with, or within other things that we automatically run on the AMI. Okay, so we want to automate it as much as possible.